This unit is about kinetics. And kinetics is the study of the rate of chemical reactions. Rate is a word that means how fast something happens. So in kinetics, we are studying how fast something happens. The other thing that we find out when we study this is information about the reaction mechanism, which is how exactly is the reaction taking place. So that's what this unit is about. It is featured in chapter 12 of your book, so you can take a look at chapter 12. We're going to be doing a little more than half of the chapter now, and then we'll do the other half a little bit later in the year. So first of all, during this unit, we're going to be talking a lot about change, and we use a triangle to symbolize change. It's the Greek symbol delta. So how do we measure the rate of a reaction? Because it's how fast something's happening, we're going to be measuring the change in something over the change in time. And you can think of this a little bit like, how do you measure the speed of your car? What is the rate of your car when you drive it? Well, the rate of your car, we usually measure in your change in miles over change in time. And so the units for driving a car, the speed of the car, are miles per hour. Miles driven in every 1 hour. A change in miles over a change in time. That's what these things are. So we're going to do the same idea for a rate of reaction. Our change in time for a rate of reaction is usually going to be number of seconds. So we'll measure the number of seconds usually, but it could be minutes, one or the other, just some sort of change in time. The real question is, how do we measure what is changing over that period of time that shows us the reaction has moved forward? So we're thinking, what can we measure that changes over a certain period of time to show us how fast the reaction takes place? And we're going to go back and look at you just took your test on solutions, and we're going to think about a reaction in solution that was on your test. And we can measure the change in concentration of something to show how fast a reaction takes place. So let's look down here. We have before a reaction takes place. In this case, we have potassium iodide dissolved, and we also have lead nitrate that's dissolved. So all the ions here are shown separately. After 20 seconds, we've had some lead iodide form at the bottom. So the concentration of lead in the solution, the lead were the reds, has decreased. We had 6 reds over here, and we have only 2 over here. So we can measure the change in concentration of lead ions as a way of showing how fast the reaction was taking place. And that's actually what we're going to do. That's the way we're going to measure concentration. It's going to be the change in concentration of a substance. In this case, it'll be the change in lead. And you have that in your notes. It says, what's the definition of a rate of reaction? And it says the change in concentration over time. And that's what this means. And we'll talk about that more. As we think about kinetics and the rates of reactions, we're going to be using collision theory. And the collision theory says that in a chemical reaction, molecules can only react if they collide with one another, if they bump into each other. So that is really important. You have in your notes, it says molecules must collide in order to react. And there's certain, even if they bump into each other, they're only going to react if they bump into each other in a certain way. So molecules must collide with the correct orientation and with enough energy to cause bond breakage and formation. So here we have 2 molecules, and they're coming together. That's what these little tails show you here. And they're going to bump into each other in a way that allows these 2 greens to bond, and then the blue and the green can separate. So they bonded. The orientation that they had was that the greens were facing each other. And they had enough energy to cause these 2 to stick together when they came together. So the idea of orientation and energy are very important. So for energy, we're going to use this word activation energy. And just as a ball can't get over a hill unless it has a certain amount of energy. A reaction can't take place unless there's a certain amount of energy, and we call that the activation energy. It's the energy to cause some of the bonds to be broken. It's an energy barrier. So this diagram is called a reaction coordinate diagram, and it helps us think about the energy of the reactants, which would be, if this is the reaction pathway, that means this is the beginning and this is the end. And at the beginning, you start with your reactants, and this is representing a reactant, and this is representing the product. And then these things are representing what happens in the middle. So in this case, you have one thing turning into another. If I wrote the reaction equation, it would look like this. This is the reaction for this picture, and the only thing that's happening here, the formula is the same, but structure is different. Here we have a carbon bonded to a nitrogen to a carbon, and later on in the year we'll talk about these bonds, and here they've switched places. So in this particular reaction, this molecule has to have enough energy so that it separates. The carbon the carbon over here kind of tilts up, and then these two pieces break apart. This area where they break apart in this reaction is the highest energy, and so we call this the activated complex. We'll memorize that word later on, not right now. And then once they break apart, it tilts over, and this carbon bonds to this carbon, and you end up with your products. This is a diagram showing the energy, how it changes throughout the reaction. One more word about that diagram, let's get a pen, is the idea of the transition state. Up here, this thing that you have at the highest energy level is called the activated complex, and the point where you have that is called the transition state in the reaction. So having talked about how reactions take place, molecules have to collide, and they have to collide with enough energy to have bonds be broken and new bonds formed. We're now going to use that information while we think about factors that affect reaction rate. What factors make reactions go faster or slower? And one of those is temperature. And if you think about this, it should make sense, because at higher temperatures, molecules have more kinetic energy, so they'll be moving faster. If these are my molecules, they'll be moving faster, and so when they bump into each other, they'll have more energy, and they will bump into each other more often because they're moving faster. So that's why temperature causes reaction rates to increase. So if you want reactions to go faster, and as scientists sometimes you want them to go faster, you usually increase the temperature and see what happens. A second thing that causes reactions to happen faster is to increase the concentration of reactants. As the concentration of the reactants increases, if there are more particles, they're more likely to collide, and when they collide, they might react. I really don't know why this picture is an example of that. So on your notes, you have pressure written down as something that will increase the rate of a reaction, and I've written that as a question here. Does a change in pressure increase the rate of a reaction? And the answer is only if it increases the concentration of the reactants. So if you change the pressure of something, let's say we had a box of gas and the particles were far apart, and you changed it so that the pressure increased, so the concentration of the reactants increased because they were more smushed together, then in that way the pressure is increasing the concentration, and that would cause the reaction to move faster or to change rate. So on your paper you have surface area as something that can change the reaction rate, and that's true because in order to react, molecules must come in contact with each other. So the more homogeneous a mixture of reactants are, the faster the molecules can react. If you look at this example, this is a diagram of two solutions that are mixed together. Red particles that are aqueous and blue particles that are aqueous. So since they're both aqueous, they can move around, and it's easy for them to bump into each other. Compare that with this picture where we have a solid something at the bottom in a green solution. The green molecules can only bump into the particles that are on the outside of this solid piece of blue, whatever it is. So they're limited in the number of particles that they can contact, and we need a collision in order to have a reaction. So this reaction might be slower than if instead, sorry, wrong color, the blue things had been crushed up and mixed in with the green things. And you know I'm using green and blue things instead of molecules. So surface area, or just having things mixed together in a way where there can be more collisions, will usually it will increase the reaction rate, because anything that can increase the number of collisions between particles increases the reaction rate. Finally, the presence of a catalyst can speed up a reaction by changing the mechanism. We will talk about this more in our when we talk about kinetics later on in the year, exactly how that works. Okay, so in the notes it says that we have defined reaction rate as the change in concentration of a reactant or product over time. The way we would write that and calculate it mathematically would be change in concentration, triangle for change, or over change in time. And oftentimes we use molarity for concentration, so it'd be that's what we use, the change in molarity, which is, and we use brackets to show molarity, over change in time. So here we have a reaction. We have, in the beginning here, we have just A, and at the end we have A and B over here. So our reaction of what's happening inside this can could be described as A becoming B. That could be our reaction. And we're going to calculate the rate of this reaction by finding the change in concentration of A divided by the change in time. So let's do that. We start out at 0 time, before it starts, and our concentration of A is 1 mole. And at 20 seconds, our concentration of A is 0.54 moles. So that would mean that our rate, I should do this in a different color so you can see it, our rate is going to be 1, well actually, we always minus final minus initial. So our rate would be the 0.54 minus 1. That's our change in concentration of A. And the time would be 20 seconds minus 0. So 20 minus 0. So we find that our rate is 0.06 m over 20 seconds. And if we simplify that, we find that our rate is equal to 0.003 m over s. That's going to be our units, molarity over s, because it's change in concentration in molarity over, in this case, time was measured in seconds. So we've just found the rate of the reaction for the first 20 seconds. Good job. Now you're going to try it on your own. So since the average rate of the reaction is the change in concentration divided by the change in time, for each of these time intervals here, we can calculate an average rate. And you'll notice that it changes over time. The average rate at the beginning is faster than the average rate at the end. The average rate decreases as the reaction rate proceeds, because as it goes forward, there are less particles to collide because there are less reactants. As it goes forward, you make more products, you have less reactants, and so there's less reactants to collide, and therefore the average rate decreases as you go forward. If we take the data from the table in the slide before and we plot it on a graph, we get a curve like this. We're plotting concentration against time. And you can see that it makes a curve. And the curve is the overall, shows the overall change in rate. But an instantaneous rate at any point where t equals 0, at any point in time, will be the tangent to this curve. So that's where your calculus is going to come in handy, although we won't be using much calculus. Yay. What we're more concerned with is measuring rates. This is supposed to be an arrow. So the best measurement of the rate of reaction is at the beginning of the reaction, because as we said, they all slow down over time. So the best measurement is from the beginning of the reaction when we are measuring rates of reaction. So in this particular reaction that's shown up here, that we have the graph for, we have a 1-to-1 ratio between this reactant and this product. So the rate of the disappearance of this reactant, and I've shown how we would measure that here, is going to be equal to the rate of appearance of the product C4H9OH. So if I would write the representation for the rate of the appearance of the product, that rate is going to be the same as the disappearance of the reactant, because as one of these disappears, you make one of these. It's a 1-to-1 ratio. But that's not always the case. And just before we move on, and I have a little minus sign here that shows that this is disappearing, because this is going to end up being negative. So if we put a negative, it all becomes positive. So when you're measuring the rate of reaction, you can choose if you want to measure the disappearance of a reactant or the disappearance or the appearance of a product. You choose what you can measure. In this case, they're equal, but they're not always going to be equal, and that's what we're going to talk about. So what if the ratio is not 1-to-1? And here we have a reaction where we have 2 hydrogen iodides decomposing to make hydrogen gas and iodine. So it's not a 1-to-1. We have 2-to-1 here. I'll rewrite this because in case these are subscripts over here. So I've rewritten it over here. And what if you've measured your rate of your I2? So we're going to put what I've written here on hold for a second, and I'm going to explain why this is true. What if you've measured your I2, and you know that the rate of your formation of your I2 over time, but you want to know how fast this is disappearing. You know this, you measured it in the lab. You want to know how fast that is disappearing. You can use stoichiometry. Okay? We know this, and you're telling me that you want to know the change in HI over time. I'm just going to cross this out for a second. I can foresee it becoming slightly confusing. So we look at our reaction, and we know that for every 1 I2 we have, we have 2 HIs. So then if we multiply this, our I2s cancel, and we find so if your rate at which your I2 is appearing, your rate at which your HI disappears will be double that. And stoichiometry can help you find the relationship. And if you look back at the reaction, that makes sense, because 2 of these have to disappear to make 1 of these. So this is disappearing at twice the rate that is appearing. So let's look at that again, because it tends to confuse people. We have a reaction right here. 2 nitrogen dioxide decompose into 2 nitrogen monoxide plus oxygen. The rate of consumption of nitrogen dioxide is equal to the rate of production of nitrogen monoxide, because for every 2 of these that get used up, we make 2 of these. So the rate of change of consumption of nitrogen dioxide over time equals the rate of production of nitrogen monoxide over time. The only difference, I put a negative here because this is going to be negative, so it becomes positive, negative, negative. But the rate of production of this is double the rate of production of this, because there's 2 of these are made for every 1 of these. So the rate of production of this is twice the rate of production of that. And you can show that mathematically. The change in the concentration of the nitrogen monoxide is going to be equal to twice the production of oxygen, because we make 2 of these for every 1 of those. So you're going to be asked in problems to be given the rate of one thing and said, well, how fast is the other thing being made? And you're going to have to go back and forth between these 2 types of concentrations. So you're going to have to use your coefficients. Like I said, stoichiometry can help you. For example, in this case, if you knew the rate of production of the oxygen over time and you needed to find out the rate of production of nitrogen monoxide over time, you know your stoichiometric ratios. For every 1 O2, you make 2 NOs, and so that would help you figure out, you would have to multiply this concentration by 2 to find out the change in the nitrogen monoxide over time. Time should stay the same. This is another way to generalize. This may help you, it may not. I'm going to cross out these. They don't. This is just, the formatting got weird. So if you have a reaction, this is a general reaction, coefficient, little letters, little a, your rate of getting rid of A over time, if you wanted to equalize that to how much, for example, how much C you made, negative 1 over the coefficient times the change in A over change in T will be equal to negative 1 over the coefficient of the change in B over change in time will be equal to 1 over C times the change in concentration of C over the change in time will be equal to 1 over the coefficient for D times the change in concentration of D over the change in time. If this confuses you, you can go back and just, as I said, use the ratios to try to figure out, and that's what we'll be practicing in class next time. So let's work 2 practice problems. How is the rate at which ozone disappears related to the rate at which oxygen appears in the reaction above? So ozone disappearing, ozone is O3, and so the rate at which ozone disappears would be minus the change in ozone over the change in time. That's how we would write the rate at which ozone disappears. Now we want to relate that to how fast this is disappearing. If this is disappearing at a certain rate, what does that mean for this? So put an equal sign over here. So what does that mean for the change in the appearance of oxygen over change in time? So we know that for every 2 ozones, we make 3 O2s. So we will have to multiply this by 3/2 in order to make it equal to what's happening on the other side of the reaction. So 3/2, that's a negative here, times the change in the concentration of ozone over the change in time will be equal to, at that particular point in time, the change in the production of oxygen over the change in time. So that is how you would relate these 2. Let's work one more problem, and then I have a question for you. So same reaction up here. if the rate at which O2 appears, and this is the way we would write that, it's our definition of rate, is 6 times 10 to the negative fifth molarity per second at a particular instant, at what rate is O3 disappearing at this same time? So this is telling us that our change in the production of oxygen equals 6.0 times 10 to the negative fifth molarity per second. And we're asked to find, at that time when this is happening, what is the change in the disappearance of oxygen over time. This is what we want to find out. So we have to relate these two, which we just did, but we can do it again. We know that if we have O2, I'm going to do it backwards now, the change in production over the change in time, and we can relate our coefficients here. So for every 3 oxygens, right, we use up 2 O3s. So that's going to allow us to calculate the change in ozone over the change in time. Now we can substitute. We have this number right here. Oops. So for this, I'm going to put in 6.0 times 10 to the negative fifth molarity per second. So this second is my time. That takes care of that. And I'm going to multiply that by 2/3. And that's going to equal this. So let's do it. So I get that equal to 4 times 10 to the negative fifth molarity per second. So this is my rate of disappearance of ozone at that particular time.